So let's look a little bit deeper into what a turbulent region involves, and like kind of do a little bit of turbulence anatomy, I guess you could say. And that'll help us then understand how we should model this system. So here's our laminar / turbulent flow again. What we want to do is look at a particular position. Let's pick a position here in the laminar region. I'm going to call this point A. And if I were to take up here, let's draw some plot, which is velocity. So this is u as a function of time. If I were to plot the velocity at that position as a function of time, what would I see? Well, it would just be whatever the velocity is at that position, constant, right? That velocity is not changing as a function of time, which is uninteresting, right? But the more interesting thing is, well, what if we did the same thing in the turbulent region? So this is a steady state problem, right? I mean, in essence, it's a steady state problem. The turbulent boundary layer is not really changing. I mean, there's sort of this chaos to it, and that chaos will fluctuate a little. But if you take the average value, the average is not changing. So if we took a point in B inside the turbulent region, and then sketch the velocity there, what would it look like? Well, it would look something like this, right? It's kind of all over the place. So this would be our, let's call this A, this is B. But the point is that there's this chaos, right? There's this like uncertainty associated with the velocity and the fluid motion at this point. And in fact, you might have it where if the flow is moving in this direction, you might have it where there's eddies that form, and the velocity here could become very close to zero at certain points, just because of the swirling of the eddies. So it can depending on the characteristics of the flow, it can be kind of all over the place there in B. But if you look at the average value, right, the average value of velocity at B is a constant. Right, there's a constant. I drew a green line there. It's hard to see, but right, there's a constant value there. OK, so if we know that's the case, I guess that helps us maybe think a little bit more about how the boundary layer is set up. So go to the next slide here. So let's look at, actually, we can look at a video. So I want to just show you what turbulent flow looks like in a really controlled situation. So here we go. So this is just a short, 2-minute video. But it's just kind of cool to visualize. This is flow. It's hard to see. There's flow over a rectangular profile. And then they have this tracer that kind of comes off of it. And what they're doing is I guess it is telling you, but what they're doing is they're starting off with a really low velocity, and then they're sort of slowly ramping up the velocity. So this is still laminar. So one thing you notice here is there is some sort of pattern to the flow. Like there's these eddies that form, and there's a pattern to those eddies. But if you tried to predict at any moment in time what the velocity is, you'd have a really, really hard time. So we as humans can see that there's patterns to it, but it becomes really difficult to have a model that specifically tells you velocity as a function of position. And then the higher the velocity that you get, the more chaotic the flow becomes. You can actually see that even though the bulk flow is going this way, there are positions where the flow is entirely reversed too, right? So, yeah, so that's kind of interesting. All right, so let's look back here. All right, so let's maybe take inventory of what's happening here. Right, you have transport of momentum and energy, but the transport is occurring by very different mechanisms for laminar versus turbulent flow. So just to summarize this in words, I guess in laminar flow, we have transport in the y direction, but that transport, because you have this like sheets flowing over each other, the only means of transport of, let's say, energy or momentum are through diffusion processes, like relatively slow diffusion processes. So you have like conduction that's occurring, you have shear stress that's occurring, but it's all sort of contained within its layer. There is a small amount of y velocity in the laminar flow, but it is sort of unimportant, as we've noted many times here. The diffusion is characterized by molecular properties, right? This is really important. So the molecular diffusion, the processes that are driving the boundary layer growth, are characterized by mu and k, right? These are incompressible flows, so rho is not changing. We'll normally assume specific heat's relatively constant. So the only thing that's driving this is mu and k. Okay, turbulent flow, on the other hand, says transport in the y direction is still present. You still have conduction. Those things don't go away. But you have these bits of fluid or globs of fluid or whatever, they're just moving, right? There's all this transport. So that mechanism of transport for energy and for momentum is much more effective than conductivity or viscosity by itself, than the molecular properties. So what happens is in the turbulent region, the turbulence, because of this really effective transport, tends to increase the effective viscosity and the effective conductivity of the fluid. Okay? So we'll talk a little bit more about that. Let's see, let's go on here. So, okay, now a little bit more anatomy here. So there's something in the turbulent region called the viscous sublayer. So you have this, the laminar forms. Once you start transitioning from laminar to turbulent, first of all, I'll say that this transition doesn't happen exactly at a point. Just like you saw in the video, it sort of starts wobbling a little, but it still maintains its characteristics. And then eventually it'll go fully turbulent, but there's a transition region. So normally you would model this as a laminar, then you'd have a separate correlation for turbulent, and in the middle of that you'd have some transition where you sort of blend together the effects. Okay, there's laminar, transition to turbulent. Once you're in the turbulent region, something called a viscous sublayer forms, and that's where there's all this motion up here, but relatively close to the wall, you're going to have a little sublayer that forms, like a relatively thin sublayer where the wall is forcing the no-slip condition. And so right next to the wall, you have to have zero velocity. Then you have this really effective transport of momentum, but that shear stress has to be kind of compensated in some way. And so right next to the surface where that shear stress is really high, the shear forces are high enough that they overwhelm the momentum, and you get this little layer that forms. So if we sketch it out, it looks something like this. Right, you have this laminar growth here. Then we have this transition region. And then you have this viscous sublayer that kind of does this. Right, so this is our viscous sublayer. So we have then two things that we have to worry about in the turbulent region. One is the thickness of this viscous sublayer, which we call delta Vs. We have also the thickness of the entire turbulent region, which is delta T, or I guess we call it delta turbulent. Right, if it's a thermal it'd be delta T turbulent. If it's momentum, delta M. So this thing includes everything. This viscous sublayer is just the little piece. So a couple things to point out. In flow over an external plate, as long as the turbulent boundary layer continues to grow, the viscous sublayer will also continue to grow. But it doesn't grow very fast, right? It's not at all like the laminar layer. It's a very slow growth. If you're in an internal flow condition, this will eventually become fully developed and stop growing, right? So that viscous sublayer, I guess, it kind of changes the way we describe things. So this is a good point. So you're aware of the viscous sublayer. Let's stop, do the top hat question, and you can think a little bit more about what these are. Okay. So let's start with this one. So the question, given that the viscous sublayer is much smaller than the turbulent boundary layer and the viscous boundary layer thickness, meaning, this should be the laminar boundary layer thickness, which of the following do you expect to be true? So would we expect the heat transfer coefficient in the turbulent region is higher than the laminar, that it's lower, and the shear stress is higher, or it's lower? So given that the viscous sublayer is much smaller than the turbulent boundary layer and the laminar boundary layer thickness, which is the following. Okay, we all set? All right, so the answers would be, let's see what you said. Did you just miss it? Okay.
I just got it.
Okay, good.
I clicked something random.
Okay, so the heat transfer coefficient, you guys think the heat transfer coefficient in the turbulent region is higher, and you think the shear stress, well, some of you think the shear stress in the turbulent region is lower. So the right answers are A and C. So heat transfer coefficient is going to be higher. Okay, so this is going to take some explanation, right? We'll go back to our notes, but it is true that the heat transfer coefficient is higher and the shear stress is higher. Okay, so why? Let's look back. Actually, yeah, I have another question, so let's do the other question first. Let me explain what's going on here. So you have the viscous sublayer, right? In the region of the turbulent eddies, or we call it the turbulent wake or whatever, that region is going to have very little shear stress that can be maintained there. It's sort of a chaotic region. So it's not really able to form consistent shear between, say, layers of fluid. So for the same reason that heat transfer coefficient's high, you have this like little viscous sublayer, that's laminar, that's your primary resistance. Then you have this really effective transport. That's for the same reasons that that's high, shear stress is also high. You have a very thin layer where there's a large velocity gradient, and then the rest is sort of washed away in that turbulence region. Okay, so let's go to the next question. Okay, so knowing what you know, let's see. Which of the following describes the Prandtl number in the turbulent region outside the viscous sublayer? So outside the viscous sublayer in that like really chaotic region, what would we think would be a good model of the Prandtl number? Everybody good? Okay. So you think it is? All right. So it will almost always be much greater, which would mean the momentum is much greater than the heat transport. It will almost always be much less, which is the reverse of that. Okay, well, I guess our anticipation is not very on. So it'll almost always be approximately 1. All right. So why? So once I have fluid that's moving by advection, I am taking that fluid, the same fluid with the same energy and the same momentum is being transported at the same time, the same distance. So the mechanisms for transporting energy in the turbulent region are exactly the same as the mechanisms for transporting momentum in the turbulent region, right? So it's got to be about 1, right? The growth of the boundary layer, thermally and from a momentum perspective, is about the same because it's the same mechanism, right? It's the same thing.